condensation in Unit 4. It's entitled, or excuse me, in Unit 1. It's entitled, It's Just a Phase. In this possibly terminal phase of human existence, democracy and freedom are more than just ideals to be valued, that they may be essential to survival. So we're talking about phases. So the learning goals are to distinguish between the different states of matter on both a microscopic and a macroscopic level. So I know you can tell the difference between a solid, a liquid, and a gas, but can you do it on a microscopic or atomic level? You should be able to relate the energy of substances to a change in phase. So, here's stuff you already know. You already know that matter can exist in three different phases, solid, liquid, and gas, and you know that matter can transition between these three states. You can melt a solid, you can evaporate a liquid. So now here's what you learned in the lab. That when you add heat to molecules, it causes them to move faster. Solid matter still moves, but it just vibrates. So if you have the solid matter right here, these molecules are moving back and forth. Liquid will vibrate, rotate, and translate. So in other words, it will move back and forth. It will rotate relative to one another, so it'll turn in a circle, and it will translate. So it'll go, this molecule will move over here, and it'll move over here, and then it'll move this way. Gas does the exact same thing, but instead of being confined to this area at the bottom of the container, a gas will actually occupy the entire container. So there are three common everyday states of matter. These states of matter vary in density, but there are also currently a lot of different exotic states of matter. There's something called photonic matter. There's quantum spin liquids and degenerate matter. There's also things called fermionic condensate. Okay, but those are things that are beyond the scope of this class. We're going to focus on the three states of matter, and we're going to add one more just to talk about. Next, it says solid. A solid on the macroscopic level has a definite shape and definite volume. So the solid says, yes, this is the shape of this gold bar. It is always that until I somehow do a physical change on that. It has very, very limited individual particle movement. So these things don't move very much. And generally, the solid is the most dense state because the molecules are the most packed in. Now, that's a general statement because it's not always true for water. On a microscopic level, the atoms are stationary relative to other molecules. So this molecule will not move relative to this molecule, but they do vibrate back and forth. But this molecule right here that I've colored red will not all of a sudden move over to this side. It doesn't work that way. They're stationary relative to one another. But they do vibrate, and those vibrations are very, very small and very, very fast. So it's a very small vibration. It's almost like on an atomic level. It's very, very, very small even at that level. A liquid on a macroscopic level is very similar to a solid in that they have definite volume. Okay, this thing right here has a definite volume. You can't take this volume and squeeze it down. Okay, if you ever try and take a water balloon and squeeze it, okay, that water balloon will just come out on the other side. Versus a regular balloon, you can actually compress a regular balloon quite a bit. So the one thing that's different between a liquid and a solid is the fact that it has an undefined shape. Okay, a liquid will take the shape of whatever the container is. So if I take this and I take this and it's the same amount of liquid, it will take the shape of whatever container holds it. Now, one thing is liquid does have free movement of individual particles. It is generally considered to be less dense than solids, and people say, yes, yes, but what about ice and water? Yes, water is one of the notable exceptions. It's not the rule. Okay, liquid gold is going to be less dense than solid gold. It just so happens that water is one of those notable exceptions. On a microscopic level, atoms are free to move relative to other molecules. So this molecule that I color right here will move over here at some point, or it'll move over here at some point. They're free to move relative to one another. Individual atoms will vibrate and translate, and they will rotate. So they will flip directions, and they'll move from left to right, and they will move back and forth as well. The one thing that makes it different from a gas, though, is that the molecule cannot escape gravity. So it can't fill up the rest of this container. This molecule can't come up here and fill up this whole entire container. Okay, gas on the macroscopic level. It's the state of matter which has an undefined shape and an undefined volume. So you can take a container of gas and you can compress it and you can squeeze it together. You can't do that with a solid or a liquid. It does have free movement of individual particles. It is by far the least dense of all of the states of matter because there tends to be a big separation between molecules in a gas. Okay, atoms are free to move relative to one another, so you have a container right here. The gas will occupy the entire container. They'll move left, right, up, down, all those sorts of things, and they can't escape gravity. They're moving fast enough where they can occupy the entire volume. So these will come here, they'll collide with the walls, and they'll go in all different directions. They're free to move relative to one another. Plasma is an exotic form of matter. It's the one we're going to talk about in this class because all plasma is a gas that's had electrons removed. So it's basically the same thing as a gas. It has undefined shape, undefined volume. The only difference is it's missing electrons. So we want to fill in the chart below. The first thing we do is we look at a solid, and we know that a solid has a defined shape, a defined volume, and it cannot escape gravity, so no escape. If something has an undefined shape and cannot escape gravity, we know that it's going to be a liquid, and it has a definite volume. Okay, a gas has an undefined, we're just going to say undefined, shape and undefined volume, and it can escape. And then that means the last one has to be plasma, and plasma is undefined, and it can't escape. Remember, the only difference between a gas and a plasma is an electron. Okay, if it's missing an electron, then it becomes a plasma. Okay, the density of ice is less than the density of water. A bottle of water is filled with ice, or excuse me, a bottle of water is filled with water and placed in the freezer. What will happen at the molecular level to change the density? So you have it occupied entirely full with liquid water. Okay, now we want to change the density. We talked about density in the first presentation. Density is mass over volume. So if it's going to change the density, I can't change the mass of the water. The mass of the water is stuck. This is how much water there is. The mass is constant. But what it can do is it changes the volume. As you put it in the freezer, it actually expands. Okay, remember, water is one of those things that actually expands as it goes to a solid. So when it does that, it changes the density. What phase of matter will have molecules moving the fastest? And that is the gas phase. Okay, gas is where they're moving the fastest because they have more energy. More energy equals faster movement. And they're also free to move about more space, so they can occupy more space as well. Okay, entropy is the number of ways that a system can be arranged. Which phase of matter has the lowest amount of entropy? So remember, how many ways can it be arranged? So if I have a container that has 3 molecules, okay, and they're all solid, this is where they're going to be. There's not very many ways to arrange that particular system. If instead I had 3 molecules that were in the liquid phase, we'll change colors and do the liquid phase, you could have them all along the bottom, but they can change places reference to one another. If you have the gas phase, you have 3 molecules and they can be anywhere in the container. So because they can be anywhere in the container, the gas is going to have the highest entropy. So that means the one with the lowest amount of entropy is going to be the solid, because there's only one way that it can organize itself, all those molecules stuck together. So next we need to talk about phase changes. So you can go back and forth between solid, liquid, and gases. When energy is absorbed, it's called an endothermic reaction. Whenever something melts, it's an endothermic reaction, which means that the temperature will actually drop as something melts. And I know that's really, really confusing to people. But what you have is you have substances that are attracted to one another. Okay, there's an attraction between these two molecules, and that's why it's considered to be a solid. In order for it to melt, energy has to take these things and break them. If there's no energy to break them, then all of a sudden it doesn't go from a solid to something else. So that right there represents what you're doing when you melt something. So it's called endothermic because you're putting energy in to breaking it. So because of that, it lowers the surrounding temperature. And I know that's really kind of confusing for people. That means the opposite. Whenever something freezes, it means energy is released because you have 2 molecules that all of a sudden there is no attraction, and now there's an attraction. Well, that attraction that appears releases energy. So the process of freezing something, with water going from a liquid to a solid, will actually produce heat. It will actually increase the temperature slightly. Now, you say, well, wait a second, whenever I make ice cubes, it doesn't get hotter in the freezer. That's because you have something that is continually cooling it down. But if you were to just take a single sample of water, freeze it, the outside temperature just above the solid will actually increase the temperature. Okay, evaporation is the process in which you go from a liquid to a gas. Um, the energy is absorbed, so it's an endothermic reaction. So you're putting energy in to taking these molecules that are kind of close together, and you're separating them and making them very far apart. So the energy is used to break the attraction. That's the reason why sweating causes you to lower your overall temperature. You put liquid on your skin, that skin evaporates, and whenever it evaporates, it's taking that energy and it's moving it away from the body as those intermolecular attractions, is what they're called, break. Condensation is the opposite of evaporation. It's the process in which you go from a gas to a liquid, and energy is released. It's an exothermic reaction. Okay, so atoms and molecules are released as energy. An example of condensation is when a glass sweats, um, and so it will actually increase the temperature of the glass as it does that. Okay, next we have sublimation. Sublimation is the process of where you go from a solid directly to a gas. There is no liquid phase, and you can see that where the snow actually becomes a gas directly. So energy is absorbed. It's an endothermic reaction. Whenever you have an endothermic reaction, you're putting energy in, and since you're putting energy in as that occurs, it's going to lower the overall temperature. So, so ice subliming, which is what you see here, will lower the temperature on the mountains. The exact opposite of sublimation is called deposition. And deposition is where the energy is released. So this is the process where you go from a solid, from a gas directly to a solid. Okay, and that's how you can make things like ice crystals or snowflakes. It says the atoms are attracting as they release energy. So it's the frost forming actually raises the surrounding temperature as you form these new attractions. So this is deposition, the process of going from a gas to a solid. Okay, which of the following best defines a phase transition? And a phase transition is a physical change because you're not changing what the substance is. It's still water, but what you've done is you've just rearranged the molecules a certain way. It says chemists often discuss reversible reaction. Match each phase transition with its reversible reaction. You see the reversible costume of Spider-Man. Okay, so condensation is the evaporation. Those are the opposite. Deposition and sublimation are opposites. One's going from solid to gas, one's going from gas to solid. And then finally you have freezing, which is going from solid to liquid and liquid to solid. It says classify each phase change as exothermic or endothermic. So we're going to put our exothermic reactions over here. We're going to put our endothermic reactions over here. Endo ones are the ones that are easiest for me because it's the ones you have to put energy into. So whenever you go from a solid to a liquid, that takes energy to do that because you're breaking those attractions. So the solid to liquid, and then liquid to gas, and then solid to gas. So now those right there are the ones that require energy. So if we go ahead and name those, going from solid to liquid is melting. Okay, going from a liquid to a gas is evaporation. And going from a solid to a gas is sublimation. Okay, so we can do the exact opposite for exothermic. So if we just reverse those, now we can say liquid to solid is exo. We can say that gas to liquid is exo. We can say that a gas to a solid is exo. Because in this case, you're forming bonds, and forming bonds releases energy. So because of that, we can say that this is freezing. We can say that this is condensation. And we can say that this is deposition. Okay, those right there are examples of exo and endothermic phase changes. Finally, it says people who sweat too much can suffer complications from heat stroke. If sweating is a cooling process, then how can excess sweat cause heat stroke? And this is a famous athlete. His name is Corey Stringer. He was an NFL player who actually died in training camp due to heat stroke. And they had to change the rules as far as how many times people can work out and so forth based on the fact of his complications due to heat stroke. And so the body is a system. It has a certain amount of water. Okay, now let's say it's got 100 kilograms of water. Okay, if it has 100 kilograms of water and it starts to sweat, what happens to the total amount of water is it decreases. So your body is really good at maintaining its temperature because it has a lot of water. And we'll talk about this later, but it is very difficult to change the temperature of water. The more water you have, the more difficult it is to change the temperature. So as a result, if you have a lot of water, your body maintains its regular temperature. But as you start to sweat to cool down, you lose a certain amount, and now all of a sudden I've got 90 kilograms of water because I've sweated out 10 kilograms of water. Well, if I only have 90 kilograms of water, it's much easier for my body to change temperature because there's not as much water. Think about how easy it is for you to boil a pot of water on your stove versus trying to boil an ocean. It requires way more energy to change the temperature of the ocean, and that's what you have here. So even though sweating is a cooling process, it leaves the body susceptible to making it easier to change the temperature. That's why heat stroke is generally associated with dehydration.